Well, good afternoon, everyone. It's great to be back. And we will continue discussion of different mechanisms for confinement of light in resonators. And I'll start by just reminding you of what we did on Tuesday. So we're discussing two different mechanisms for confinement of light. Total internal reflection, which was a review for most of you, and also we started discussion of the distributed Bragg reflection and photonic crystals. I will not really review total internal reflection since I'm sure you had seen that also earlier before Tuesday, but I will spend a little bit of time reviewing what we did last time regarding distributed Bragg reflection, and then move on a little bit further and introduce some new concepts. So photonic crystals are structures with periodic dielectric constant. They confine light by distributed Bragg reflection. We went through this cartoon image of distributed Bragg reflection where all the partial reflections from the structure add up in phase, and that leads to larger reflectivity in the direction of propagation. And you can also achieve that in structures that are also more than one-dimensional, more than just regular distributed Bragg reflectors shown here. So that's a cartoon-like image where you design the structure in such a way that all the reflections of the wave add up in phase, right? And in two-dimensional case, you can do that in basically any direction propagation inside of the structure. And in three-dimensional case, you can do that even in any direction in 3 dimensions. Then we also looked into what is happening inside of the structure once you are exciting it with something with an electromagnetic wave for which distributed Bragg reflection is satisfied. We said that that corresponds to the frequency region that we refer to as the photonic band gap. That's where propagation inside of the structure cannot happen. We see from these movies that when you excite the structure with the frequency inside of the photonic band gap, you still have some finite penetration depth. But there is no net energy flow in the direction of the mirrors. And in two-dimensional photonic crystals of finite depth, these planar photonic crystals, vertically we use total internal reflection for confinement. And today we'll talk more about this band diagram or dispersion diagram and how photonic band gap appears and properties of the band diagram. So don't worry if you don't understand everything now, but it's completely analogous to energy band diagram for electrons in semiconductors. We also started reviewing real space lattice and reciprocal lattice. This is exactly the same as condensed matter physics. Any periodic structure, crystal for light or crystal for electrons, can be represented with a lattice. You describe it with primitive real space lattice vectors, which we label as A1, A2, A3 for 3 dimensions. And then based on that, you can find reciprocal space lattice vectors from this relation here, that the dot product between reciprocal space vectors and real space vectors gives you 2 pi times Kronecker delta. And using that relation, we found reciprocal lattice corresponding to rectangular real space lattice. Of course, dimensions would be in 1 per unit length coming from this relation. And the alignment of reciprocal space lattice vectors to real space lattice vectors come from simply satisfying this condition. And we also mentioned that the introduction of the reciprocal space lattice is important because we will be introducing Fourier transforms of the dielectric constant. It's a periodic function of space, and that's where reciprocal lattice comes into play. And one more term we introduced or reviewed for many of you is the Brillouin zone. First Brillouin zone is obtained by drawing perpendicular bisectors to nearest neighbors connections in the reciprocal lattice. So you draw reciprocal lattice, then you draw perpendicular bisector planes to nearest neighbor connections, and whatever region of space you define in that way is your first Brillouin zone. And first Brillouin zone is important because the distance between any points, any 2 arbitrary points in the first Brillouin zone cannot be really described with the reciprocal space lattice vectors. Reciprocal lattice vectors. So if you pick any point there and add any arbitrary reciprocal lattice vector, you are going outside of the Brillouin zone. And that's the reason why it's introduced that way. Okay. I'm still going through a review and just a couple more slides, and then we'll go into the new material. So feel free to interrupt if you have any questions, because we'll be building up on this for the rest of the lecture today. Then using everything that we know about periodic structures, photonic crystals, and that's the fact that the dielectric constant is periodic in space in up to 3 dimensions. So they have discrete translational symmetry. That means you can expand the dielectric constant in Fourier series, right? If it's one-dimensional, it's one-dimensional Fourier series. We'll be doing that later in class today and calculating actually photonic band gap for one-dimensional crystal from that master equation we introduced last time. But in the general case, it's a 3-dimensional Fourier series because you have 3-dimensional periodicity of the dielectric constant. Expansion is over these coefficients that are labeled with G, and G is the basically reciprocal lattice vector, arbitrary reciprocal lattice vector. And we'll see, we will review that for one-dimensional lattice last time. We'll do it again later today. So that connection between 3-dimensional Fourier series and one-dimensional Fourier series will be clear. But again, for any periodic function, you can expand it in Fourier series over basically reciprocal lattice vectors. That's where reciprocal lattice vectors come into play. They're basically defining Fourier coefficients. And Fourier coefficients are calculated by calculating this integral over a volume of the unit cell. So that's just definition of the 3-dimensional Fourier series. And then we also know that for any system, you have to satisfy Maxwell's equations. Here we have non-magnetic material, so mu is mu naught. We have no currents, no losses. Epsilon is real, but epsilon is periodic. That gives you the following wave equation. And then by substituting Fourier series for epsilon, since epsilon is periodic, and by substituting Fourier integral for electric field, which is always possible for any function, you can find Fourier transform, you can obtain the following master equation. And the 2-line derivation is in the course reader. So this master equation, we started discussing it at the very end of the class last time, but we'll spend more time on it today. And in particular, we will use it to calculate size of the photonic band gap and band diagram for one-dimensional distributed Bragg reflector. However, you can use it actually to calculate also 3-dimensional band structure. And we will also use it to kind of find some interesting properties of photonic band gap and photonic band diagram in general. So what is this master equation? Any questions about things so far, or everybody is okay? You can react at the bottom by raising thumb or raise thumb in person for those of you who I see there. Great. Okay, so let's go back to this master equation, right? So I rewrote it here. Sorry, I didn't write vectors, but all K's and A's are vectors, right? It's the same equation as on the previous page. So here is our master equation, right? And master equation basically connects Fourier coefficients of epsilon, right? So that's epsilon G. It connects K. K can vary in space. You can write master equation for arbitrary K vectors in the K space, right? It holds for any K. Omega is frequency that you picked when you wrote your wave equation, right? So we're writing this for monochromatic wave. You can change omega. Again, you can go from 0 to infinity and see if there are solutions for particular omega and K. And A of K are coefficients in the Fourier series expansion of electric field, okay? So this equation, you can rewrite for arbitrary Ks, but let's rewrite it for whatever K you chose at the beginning, right? So let's say you pick one specific K in K space, okay? Any point in K space that you would like to define master equation for, you write it here, and then rewrite it for K minus G prime, where G prime is some arbitrary reciprocal lattice vector that you picked, okay? So then you rewrite this equation for K minus G prime, and here it is, okay? What is interesting here? It's interesting that the second equation, again, spans through the same A coefficients as the first equation. Why? Because every single A that you have in the second equation and in the first equation would be on the reciprocal lattice that is drawn in the K space around whatever K vector you picked. Is this making sense? This is usually the hardest thing to pick up, right? So we can spend a little bit more time on that. So you write at the point K that you picked, and then at the points K plus G, where G is a reciprocal lattice vector. So you pick your K, and then you draw reciprocal lattice around that K, okay? and you have a grid of A of K's, and that on that reciprocal lattice that is connected via this equation. Is that making sense? Okay, and then you write second equation. I mean, you just rewrite master equation for K minus G prime, where G prime is whatever reciprocal lattice vector you picked. And then when you look at this equation, it basically inside of it itself has, again, the same set of A's as the first equation, because they're just translated by G prime, but it's the same reciprocal lattice, just translated by G prime, which is also reciprocal lattice vector. So if you take reciprocal lattice, translated by any reciprocal lattice vector, it's the same lattice. Is that making sense? So it's the same set of A coefficients. Or you can rewrite it for another reciprocal lattice vector, G double prime, and here it is. And again, it's the same set of coefficients. It's the same as the initial lattice, but just translated by another reciprocal lattice vector, which is again going back to the same reciprocal lattice. Is that making sense? Okay. So, I mean, maybe we go back to the drawing of the reciprocal lattice here, and it will also get clearer when we are actually solving this for one-dimensional space. Here is our reciprocal lattice. If you translate it by any arbitrary reciprocal lattice vector, and reciprocal lattice vector G would be some combination of 2 pi over A1 and 2 pi over A2, you end up with the same lattice, right? Okay, so that's what we're talking about. Translation by G prime, this may be G prime, is basically the same lattice. So if you just define coefficients in the K space on particular reciprocal lattice, it's actually the same set of coefficients once you translate by G prime or G double prime. So why am I kind of emphasizing this? I'm emphasizing this because when you rewrite master equation for as many K minus G prime, K minus G double prime, or any other arbitrary reciprocal lattice vector that is giving you translation relative to the original K that you picked, you just couple still the same set of A of K coefficients. Okay, so you have continuous K space, but whatever K you pick at the beginning, that would define particular reciprocal lattice around that K, and you would only sample A of K coefficients on that grid with a certain set of equations. But E-field expansion is along continuous A of K, right? We have a Fourier integral that goes from 0 to infinity in all directions in K space, right? But this master equation only couples discrete values of A of K on a reciprocal lattice. Okay, so they're quite different. But anyway, I can rewrite this master equation as many times as I like, and I will always couple only the coefficients on a specific reciprocal lattice that is drawn around K point that you picked. And all of those equations can be written as some matrix, which depends on K, omega, mu naught, epsilon, G, right? Everything that you have in these equations other than A of K. And then here you have a vector that would basically give you all the A of K coefficients. Okay, so you have A of K for the first, A of K from the first equation, and then A of K minus G prime, A of K minus G double prime. All of them actually appear in all of the equations, but they're just coefficients of A of K sitting on the reciprocal grid. And on the right-hand side, we have 0, which means that we have a homogeneous system of equations. And again, if you have a hard time following this, it will get clearer when we talk about one-dimensional system of equations. We'll repeat everything just for one-dimensional K. So we have some matrix that depends only on K, omega, mu naught, epsilon, G, Fourier coefficients of epsilon. Then we have all of these Fourier series expansion coefficients of the electric field solution in the system at the points in the K space that are sitting on the reciprocal lattice around the K, a certain K point that you picked, and that's equal to 0. As any homogeneous system of equations, this one has a non-trivial solution, which means solution where the coefficients that you have here, A of K, are not all equal to 0, when this determinant of the matrix that you have on the left side is equal to 0. Okay? So if determinant of this matrix is equal to 0, what does that give you, right? When you calculate determinant, you obtain some function, some kind of polynomial depending on these coefficients. And that function would depend only on K, omega, mu naught, epsilon, G, and that would have to be equal to 0. Okay, So what do we have here? We have mu naught, which is fundamental constant. We have omega, which is whatever frequency we picked, but we can also change it. And we have epsilon g, which are Fourier coefficients for our periodic structure. So calculating determinant for non-zero, non-trivial solution of the field would give you basically function, which gives you relations between omega and k for a given structure where you have non-trivial solution for the field. Trivial solution for the field would mean that all the Fourier coefficients are 0, and that means field is equal to 0, but non-trivial solution for the field means that you have non-zero field in the structure. So this was a lot of math, but let's kind of go back to the beginning to see what this actually means. So this means that essentially from the master equation, you can pick certain frequency, omega, calculate determinant of the system that is function of omega and k. You also need to calculate Fourier coefficients for your periodic epsilon, but you can do that because you know how epsilon looks in space. And once you write this function, you will find combinations of omega and k for which you have some non-trivial field in the system. And that's exactly a photonic band diagram. Okay? That's exactly that relationship between omega and k that we drawn where you have non-trivial solutions for the field. So that's what we'll do today for one-dimensional photonic band diagram, but in more general case, you can do it also for two-dimensional or three-dimensional, and things will get clearer later. Any questions about this?
Yeah, so how do you truncate? So it seems like that would be like an infinite.
Absolutely, right? That's an excellent question. So that will, of course, it's an infinite system of equations, homogeneous system of equations relative to coefficients. But depending on where in space you are calculating dispersion diagram, you can truncate it at a certain number of coefficients. So for example, for today, for one-dimensional distributed Bragg reflector, we'll be calculating band diagram around the so-called edge of the Brillouin zone, which is pi over 8 point. And it turns out that there, we can truncate it to system of two equations. Okay?
Okay, cool, thanks.
So it depends, it really depends. So the bottom line is really depends on the region of the band diagram which you are calculating. Okay? Any other questions? Yeah?
I have a question about why do you only pick, so why the master equation only allows you to focus at one single k? I can understand that you're trying to make some like Venn diagram like that. So this is k.
Yes.
And you're trying to only focus on here, and all the value would be the eigenvalue of
yes
omega k relation.
Yes.
But why the master equation only focus on this?
K can vary anywhere in space from basically 0 to infinity if you're writing it for one-dimensional system. But we will prove 2 slides from now that you only need to basically write this equation for K inside of the first Brillouin zone, because we will prove it that all of the solutions for the field outside of the first Brillouin zone have to be the same, kind of periodically repeat as the ones in the first Brillouin zone. So you write your equation for K, and when you look at this master equation, you can say K can have any value in 3-dimensional space, okay? Yeah. For any value that you chose, you can write this equation, and then you can rewrite it for values in K space that are translated by reciprocal lattice vector, and you're building up your system of equations that way, okay? But you will prove in a moment that you don't need to do it for the whole K space, you just need to do it for the first Brillouin zone.
Yeah, so why this is the best strategy to construct a band structure?
It is not necessary, depending on what you want to do. This is the strategy that will give you some analytical solutions for how large the band gap is and what the penetration depth would be, right? So in a moment, we will solve one-dimensional band diagram, and we will see exactly the size of the band gap as a function of the Fourier coefficients. For example, for the structure, we'll see what is happening in the field. I mean, for example, you can also, once you find where your photonic band gap is, you can go back to this system of equations, write omega, which is inside of the photonic band gap, and then try to solve for k's for which you have non-zero field. And you will see that you will obtain complex k's, which means that you have exponentially decaying fields, right? So this strategy allows you to see exactly analytically, of course, with some approximations, what is happening inside of the periodic structures. Of course, you can use numerical methods, but numerical methods are not really giving you intuition on the size of the photonic band gap as a function of Fourier coefficients and so on.
Yeah.
Does that make sense? Yes. But for now, you can say, well, K is continuous, can be anywhere in space, right? And omega can go anywhere from 0 to infinity. But these systems of equations that you are writing are going to constrain omega K relation for which non-trivial solutions exist. Okay? All right. Any other questions before we move on? Okay, so just a summary of what we did here, right? So just what we did on the previous slide, we can write master equation. Each master equation couples a coefficient A of K. So again, this is a Fourier series expansion for the field with all the coefficients that are sitting on the grid on the reciprocal lattice around that K. So only A of K, which are separated by reciprocal lattice, are coupled, right? Although A of K is kind of continuous in K space, by writing this system of equations, you're just sampling in that K space reciprocal lattice of A of K coefficients, right? But remember again, your arbitrary field solution in the system is a Fourier integral over continuous A of K, right? But then each system of equations gives you just coefficients that are on certain reciprocal lattice, which means that you can decouple your electric field into independent solutions, each one of them being solution of one specific system of equations that you're writing for certain K, and then the other ones would be independent of that, right? So this is what we're doing, and I'll repeat what I just said, right? So arbitrary electric field in the system is a Fourier integral over A of K, where A of K is a function, continuous, some arbitrary continuous function in space. But then each system of equations that I write from master equation couples only coefficients that are sitting on the reciprocal lattice, okay? Which means that I can introduce new modes that are only depending on these Fourier coefficients sitting on each particular reciprocal lattice, okay? They're decoupled from each other because they're solutions of very different systems of homogeneous systems of equations that you are writing there. You can repeat writing of your master equation many times. So more normal mode written for a particular capital K, right? And capital K is one specific value of the K vector that you chose, would be a superposition over Fourier coefficients that are sampling reciprocal lattice around that capital K, right? Instead of this Fourier integral over continuous K. And of course, this is not the arbitrary solution in the system. I can write these normal modes for any capital K in K space, and then the total field would be superposition of these normal modes. But I call them normal modes because they are solutions of completely different system of equations that I wrote based on the master equation. Okay?
So if I think the decomposition of E as a planar wave decomposition, then do I need to consider the evanescence field when if we're talking about very far away?
Yeah, exactly. And you will see in a moment, actually later today, if we have time, we will see that exactly you will have, if you pick omega inside of the photonic band gap, the master equation will be satisfied only for complex K. There will be imaginary part. So you will have evanescently decaying fields. So if you pick K, if you pick omega, which is outside of the photonic band gap, then you will basically just express arbitrary field in terms of these solutions that we call normal modes. And in a moment, you'll see that they are something that you've seen before in condensed matter physics and other classes, right? Arbitrary field will be decomposed into them, and they're not evanescent modes. They're propagating modes. But inside of the photonic band gap, there will be evanescently decaying modes. Okay? And I'm not going to spoil, I don't want to give you a spoiler now. You'll see in a moment that these modes, normal modes, are something that you've already seen. Okay?
So,
and we'll show it on the band diagram.
So normal modes only consider one single K inside.
For each K, right? For each K,
yeah.
You can write a normal mode. and for, of course, for each k and for each frequency. And you know, when you, I'll give you a little spoiler, right? But not a big spoiler. It'll be more interesting if we just prove some things right now. But if you go back to the band diagram that we were showing here, right? I mean, these letters here just denote different combinations of kx and ky, k vector in the k plane, right? And this is frequency, okay? So what we're doing here is we say, okay, I'll pick certain frequency, let's say this one, okay? And for that frequency, and for whatever k I want, and whatever k I want would mean continuous k that I pick here, I write master equation, okay? And I write it for k, k plus g prime. And then I look whether there are solutions of that master equation that exist. If there are solutions, then there would be circles here on this diagram. If there are solutions with real k, right? If there are no solutions, then there are no circles on the band diagram, okay? But, you know, of course, those of you who took condensed matter physics know that on the k x-axis of this band diagram, I just plotted first Brillouin zone. There is a reason why we're doing that. I'll explain it in a moment. We don't draw it from 0 to infinity. Okay, so going back to our normal modes, right? I just, you know, arbitrary field in the system is a Fourier integral, but I can always decompose it into these normal modes because they're solutions of independent system of equations, and each normal mode is just adding up Fourier coefficients sitting on the reciprocal lattice for whatever k you picked, and that k would be in the subscript of the mode, okay? So let's see some interesting things of these normal modes. Okay, so let's go back to one normal mode. Let's say I write a normal mode for coefficient k, right? And this is capital K. And it's a superposition of these Fourier coefficients. And then here, I mean, this is how they're defined. So let's now see what would be E normal mode of R plus A, right? So I'm just checking for periodic properties of these normal modes, right? So what is E of R plus A? You just plug in R plus A here, right, in the exponent, and then you use the property that G dot product A is what? What's G dot product A?
2 pi.
2 pi times n, some integer, right? Because G is not necessarily a primitive reciprocal lattice vector. It could be some arbitrary reciprocal lattice vector, but it's 2 pi over times n, right? Which is not changing the result because this part would be 1, right? And then you just rewrite, just cancel that out, keep e to the I k dot a outside of this and rewrite everything. So what is this thing here? This thing here is the same thing as what we had at the beginning, ek of r, right? So ek of r plus a is ek of r times e to the I k dot a. Have you seen this before?
Bloch condition.
Bloch condition, right? So these are exactly Bloch or Floquet modes, right? So this is Bloch or Floquet theorem. So these normal modes, right, basically have to satisfy Bloch theorem. And we didn't really assume this. This is a consequence of the fact that there are solutions of these in master equations that are written for periodic dielectric constant. They simply follow from the equation that the electric field in the system has to satisfy. And these independent solutions for the field have to satisfy Bloch theorem. Okay? Let's see something else, right? So what other things do they have to satisfy? Let's look at the Bloch mode for the field, which we can write as e to the I k dot r times this thing under the sum. The only thing that I did here is I took out e to the I k dot r outside of the sum. Okay, and then this thing under the sum, it turns out has to be periodic. And sometimes people write it as uk of r. And it's easy to show that uk of r is periodic. That's another way to formulate and to write Bloch theorem, right? So you have some periodic function times plane wave. But it's not different than what we had on the previous page. It's the same sum over Fourier coefficients written on the reciprocal lattice times these plane waves that are written again on the reciprocal lattice. So now I'm interested in seeing what would be the Bloch mode for k plus g1, where g1 is some arbitrary reciprocal lattice vector. Okay? Let's say you have a Bloch mode at some value of k, capital K, and you're interested in seeing what would be the Bloch mode at k plus g1. I can just write the whole thing directly, but instead I'll just write this periodic part, which is in the red rectangle, at k plus g1, okay? And you just substitute k plus g1 instead of capital K. Then you can pull out g1 outside of the sum, reorganize everything, then substitute that g minus g1 is another g. This whole thing here is again your u, right? So the whole thing is basically u of k times e to the minus I g1 dot product r, right? So it's a very simple math. In 3 steps, you can show that this periodic part of the Bloch mode or periodic part of the normal mode is this at point k plus g1 is the same as the periodic part at the point k times this plane wave defined for the k vector equal to reciprocal lattice vector g1. And then if you're interested in the whole normal mode at k plus g1, then you just have to multiply that with plane wave corresponding to k plus g1, right? So Bloch mode or normal mode at k plus g1 is this periodic part at k plus g1 times plane wave at k plus g1. And then you plug in what you found in the previous line, cancel out the g1 terms, and you obtain that everything is just equal to uk of r e to the ik dot r, which is just the normal mode at the point k.
So is the normal modes definitions UK or AK?
Normal mode is E of K. U of K is just the periodic part of the normal mode. So sometimes when you define the whole thing is the normal mode or what we call Bloch mode. We just proved that it satisfies Bloch theorem. But every Bloch mode can be represented as basically plane wave corresponding to its K vector times the function that is periodic with periodicity of the lattice. And you can easily show that once you pull out e to the ik dot r outside of the sum, the thing under their sum has to be periodic with periodicity a. I mean, you can kind of see it already. If you plug in r plus a, again, you have the same thing, g dot a, which is 2 pi n, right?
Mm-hmm.
Okay.
Yeah.
So what did we prove here? What does this mean physically? Normal mode corresponding to some point k in k space, capital K, is the same as the normal mode corresponding to the point k plus g1, where g1 is arbitrary reciprocal lattice vector. What does this mean? And we can go back to the question that you asked me, right? I mean, we just discussed a moment ago what was happening, for which case do I have to write these solutions, okay? But now I proved that Bloch mode or normal mode for whatever k you picked would be the same as for k plus g1, where g1 is reciprocal lattice vector. If this is true, do I have to really calculate Bloch modes outside of the first Brillouin zone? No, because every point outside of the first Brillouin zone can be calculated as the point inside of the first Brillouin zone plus some reciprocal lattice vector, okay? This is telling you that everything is the same outside of the first Brillouin zone, periodic with periodicity of reciprocal lattice. So once you have all of your Bloch modes in the first Brillouin zone, you're fine. That's all that you need, which is when we plotted Venn diagram for photonic crystal, or when people plot it for semiconductors, they just do it for all the points inside of the first Brillouin zone. To be more accurate, they don't do it for the whole first Brillouin zone, they do it for the so-called irreducible first Brillouin zone, because even inside of that first Brillouin zone, there are regions that are by symmetry the same, identical to each other, right? So you can kind of cut that rectangle that we had in the first Brillouin zone into triangle, which is 1/8 of it. Is this making sense? Okay. All right, so just to summarize what we did so far, right? So what did we do? We just started from Maxwell's equations, right? We wrote them for periodic epsilon. Any periodic function can be represented in Fourier series. We used the Fourier series expansion of that periodic function, and we wrote equations. These are master equations for the system that field has to satisfy. And since different Fourier coefficients in the field expansion that are written on different reciprocal lattices satisfy completely independent systems of equations, then you can decompose the field into these normal modes that we found out basically are Bloch modes. They satisfy Bloch theorem. And they're completely periodic with the periodicity of the reciprocal lattice. In other words, you just need to have them inside of the first Brillouin zone, and outside they're exactly the same. You don't need to recalculate them. We did this for electric field, but of course you can do exactly the same thing for magnetic field. You can write wave equation for magnetic field, and you can introduce normal modes for magnetic field, and they would satisfy again the Bloch theorem, right? And you can write Bloch theorem either in the way we wrote it before, that electric field at the point r plus a would be e to the I k dot a electric field at point r, or you can decompose the electric field into this periodic part times plane wave, and then automatically this is satisfied. Okay, so one more comment before we move on, right? So these are just normal modes of the system. These are independent solutions for the field. What about the arbitrary solution for the field, right? When we started this whole business of calculating what is the solution for the field in the system, we wrote the field as the Fourier integral over A of k, where k was going everywhere in the k space, right? But these Bloch modes are just sampling some reciprocal lattices. So there are solutions for the field, but how would you find arbitrary solution for the field? What do you have to do? You have to go back to your normal modes, which are basis for solving the field, and add them up, right? So you would expand your arbitrary field in terms of the Bloch modes. They're basics for expanding the field. And I'll summarize that, and then we will move on to solving the one-dimensional master equation, where all the things will get even clearer, right? I thought it makes more sense to do it for three-dimensional arbitrary case, and then we actually solve it for one-dimensional case. So going back, here is our master equation, right? This equation can be rewritten for arbitrary k, and then for arbitrary k plus g, where g is reciprocal lattice vector. By rewriting this, you can construct this homogeneous system of equations with respect to A of k, Fourier coefficients of the field. And then for non-trivial solution, you have to have determinant of your matrix being equal to 0. And that determinant only depends on omega, k, mu naught, and Fourier coefficients in the expansion of epsilon. So what does that mean, right? So if particular normal mode exists in the system, and is not just field is 0 everywhere, that means that determinant of this system would be 0, which would give you some relation between omega and k that you have to solve for finding non-trivial field, okay? So if there are non-trivial coefficients of A of k, that means that there is a Bloch state in the system, and then determinant that you have to solve would give you a combination of omega and k for which that Bloch state exists. So when we plot this so-called band diagram here, what do? We just plot the combinations of omega and k's for which non-trivial solution exists. And each point here would correspond to a certain Bloch state, right? That's what we plot. Each point here corresponds to certain Bloch mode for combination of omega and k for which we're calculating band diagram for which non-trivial solution exists. Inside of the photonic band gap, there is no real combination of omega and k for which solution exists. If you will see in a moment, if you plug in omega inside of the photonic band gap, try to calculate for k, you'll find complex k, which means that the fields would just exponentially decay. They're evanescent Bloch modes. We've also learned that you don't have to repeat this for k going from 0 to infinity in three-dimensional space or in one-dimensional space, because Bloch modes outside of the first Brillouin zone are exactly the same as in the first Brillouin zone. Bloch modes for whatever given k would be the same as k plus g, where g is arbitrary reciprocal lattice vector. So when people plot these band diagrams, they just do it for the first Brillouin zone. So these letters here that you have here correspond to high symmetry directions at the edges of the irreducible first Brillouin zone. But irreducible first Brillouin zone is just part of the first Brillouin zone. You reduce it by symmetry, right? Because it turns out that you don't even need all the solutions in the side of the first Brillouin zone. And as one extra thing here, you see this is a two-dimensional diagram. What we're doing, I mean, this is for the diamond lattice. We're going in certain directions along the edges of the first irreducible Brillouin zone. So we're not even doing it for all combinations of K inside of the first Brillouin zone. This is because you can prove that extreme points of the band gap photonic band diagram occur at those high symmetry directions. But we'll analyze that a little bit later. I mean, when you look at the band diagram, these two-dimensional pictures that people plot either in condensed matter physics or for photonic crystals, they typically only care about high symmetry directions, and they typically only care about the size of the photonic band gap. But there are applications where you actually don't only care about size of the band gap. You're also interested in propagation for some arbitrary points inside of the first Brillouin zone. Like, for example, super prism applications or propagation inside of the photonic band and refraction and so on. So in that case, you have to calculate this band diagram for all K points inside of the first Brillouin zone. This is just in addition to what we said, but it will get clearer a little bit later. Okay? Any questions?
It seems that we're solving for normal modes in frequency domain, but I'm wondering if you can also have normal modes in the time domain.
Normal modes in the time domain. Can you clarify your question? What would that exactly mean? I mean, these are, of course, time-dependent fields. You are solving it for particular monochromatic solution, right? I mean, you're talking about finding another basis for the problem in time domain, right?
Mm-hmm.
Yeah, I'm here, you're right. We're just defining solutions. We're finding normal modes or the basis for expanding particular eigenfrequency, right? So if you actually have arbitrary solution for the field at a given frequency, you can expand it in terms of the Bloch modes. That's the basis for your problem. But going back to your question, that's not always the perfect basis for expanding the field in the system. But for now, if you are interested in, since we're just studying what is happening inside of the periodic structures and the origin of the photonic band gap and so on, it's actually the best basis for analyzing the size of the photonic band gap, right? If you are looking at the propagation outside of the band gap, there are other bases that may be potentially more useful. Okay? Yeah.
Thanks.
Any other questions? Okay, so now we can actually start. Let's set up the problem. Sorry, I think maybe someone needs to mute. Maybe I have some. Okay, make sure. Good. There's some feedback coming. Let's now go back to the same thing that we did for master equation, but solve it for one-dimensional periodic medium. And I'll set up a problem and then we'll solve it after a brief break, right? So this is now easier mathematically than what we had before, but exactly the same problem. Instead of three-dimensional periodic structure, we have one-dimensional periodic structure, periodicity A. Periodic epsilon is periodic with periodicity A. You can write it in Fourier series. Okay, here is your Fourier series expansion for one-dimensional periodic function. I mean, it's the same as the three-dimensional, but right now we have your reciprocal lattice vector, which is just 2 pi over A in the z direction of propagation. You just write it, all the Fourier coefficients written and all the reciprocal lattice points, which are just discrete points, n times 2 pi over A. And then also you calculate Fourier coefficients by integrating periodic function from 0 to A, right? And normalizing it with A. So this is just vanilla Fourier series, right? For one-dimensional functions, okay? So we do all of that. And then, sorry. And, you know, all the conclusions that we had for general form three-dimensional master equations still hold, right? We know that solutions for the fields would satisfy Bloch, would also be decomposed into Bloch modes, right? Because we solved it for the general case. If you reduce it from 3 dimensions to 1 dimension, things still hold. So we will have Bloch modes, but these would be one-dimensional Bloch modes. And these one-dimensional Bloch modes would be written as shown here. They would have some periodic part, and they would also have plane wave part, and plane wave part would correspond to particular point K in K space, right? And periodic part would be periodic with periodicity A. Okay? Is this okay? Everybody okay? Okay. So great. So we have one-dimensional structure. We know that conclusions of our analysis hold because you can actually write master equation. Solutions would satisfy Bloch theorem. They would be one-dimensional Bloch modes. These one-dimensional Bloch modes can be written as the plane wave times the periodic function. And this periodic function, if you want to go back and see how we wrote Bloch modes for three-dimensional function, you can also write it as superposition of Fourier coefficients written at the reciprocal lattice. But what is our reciprocal lattice? Reciprocal lattice would basically just be one-dimensional lattice where nodes are separated by 2 pi over a, right? It's a one-dimensional space. So you just pick certain kz for which you write your Bloch mode, and then you sample Fourier coefficients at the reciprocal lattice, which is just separated from that k point by 2 pi over a. And here you have also expansion in terms of that coefficient g. Okay, and also our master equation that we wrote for three-dimensional case could be reduced to one-dimensional case. This is how it would look like. Here, instead of arbitrary three-dimensional k vector for which you're writing master equation, you will have a one-dimensional k vector. That one-dimensional k vector would be in the z direction, right? That's the direction of the periodicity. And then we picked that our electric field is x-polarized. And the fact that electric field is x-polarized would lead to this change in sign here, because you will have cross product between z, x, and then z again here, right? And then all of your Fourier coefficients are basically just written on this one-dimensional reciprocal lattice. And then your Fourier coefficients for epsilon would also be labeled with particular coefficient n, which corresponds to the index of g vector on the reciprocal lattice. So this is epsilon n corresponds to n times 2 pi over a. So this is relatively simple. It's basically just simplified form of the three-dimensional master equation. You just write it in the one-dimensional case. So here is your one-dimensional master equation now, right? So just reduced from 3D to 1D. The whole idea behind this was that you can use this to find dispersion diagram, okay? So again, this master equation here, written for whatever kz you chose, couples only Fourier coefficients for the expansion of the field written on the reciprocal lattice around that kz. So you see it's only a of kz minus n over n times 2 pi over a, and so on, right? So if you pick along the axis certain value of kz, then you will draw this reciprocal lattice, which is just the points that are separated by n times 2 pi over a relative to that point, and you'll be sampling Fourier coefficients at those points. So then, you can start from this and write this infinite system of equations for coefficients a of k. And then by looking at the determinant of that system of equations, you can find the relation between omega and k for which non-trivial solutions exist. And that is what we will be doing after a brief break, okay? If you have any questions, I'm happy to pick them up now during the break. Otherwise, you're free, of course, to go. Come back in 5 minutes. Okay. Hello, do we have everyone back online? Hope so. Good. It's very hard to tell when people are back or not, but let's keep going. All right, 5 minutes are up. Okay, good. So going back to our one-dimensional master equation, right? Just to remind you, we are now solving master equation for one-dimensional periodic structure. And things should be much simpler, right? So we already went through the exercise for arbitrary three-dimensional periodic system. We had some discussions of that. Now we just rewrote everything for one-dimensional case, and all the conclusions from 3 dimensions should still hold in 1 dimension, such as that Bloch states should exist, but they are one-dimensional Bloch states, right? But here I'm just writing master equation for 1 dimension. And this is how it looks like. It looks simpler because you don't have these cross products anymore. Just calculate cross products. There is one flipping sign coming from Z cross product, Z cross X. But other than that, it's all the same. And you also write on the Fourier coefficients that are on this one-dimensional reciprocal lattice, which is just a grid of points on the k-axis separated by 2 pi over a, okay? As in 3 dimensions, we can rewrite this equation for arbitrary k plus g, where g is arbitrary reciprocal lattice vector, right? So that would be k plus some coefficient times 2 pi over a, right? Where you can vary that integer coefficient, right? And again, you start with a certain kz that you picked, and kz could be anywhere on the k-axis from minus infinity to plus infinity. But by now we should know that you actually should only do it for the points that are inside of the first Brillouin zone, because outside of that, it should be periodic. So by the way, what should be the first Brillouin zone for one-dimensional periodic structure in K-space? What is the first Brillouin zone?
2 pi over a?
Exactly. So from minus pi over a to plus pi over a, right? Or from 0 to 2 pi over a. It doesn't matter. It's like 2 pi over a of width. And you can pick any width you like, but generally we go from minus pi over a to plus pi over a, okay? So then you can pick any k from minus pi over a to plus pi over a, or actually even better from 0 to 2 pi over a, because irreducible first Brillouin zone would be just from 0 to pi over a, right? 1/2 of that whole first Brillouin zone, because everything will be symmetric, and you can prove things by symmetry arguments. So anyway, here is our master equation. I can rewrite it for other k plus minus some integer coefficient times 2 pi over a, and we'll see in a moment what system of equation that leads to, okay? But before we do that, we'll also make some approximations. And someone asked me earlier on, I think Alex or Yishu, how are we truncating this system of equations? Because of course, if I write this equation, there are infinitely many coefficients that are coupled, right? And those are, for whatever choice of k you have, there'll be infinitely many coefficients written on the reciprocal lattice, right? And I have to write this again for all of these different reciprocal lattice vectors. So there'll be infinitely many a of k written on the reciprocal lattice. Well, if we make some approximations, then we can actually truncate the system of equations and solve it analytically, which is what we want to do now. Okay. So we will make some assumptions about the system. For example, we'll assume that we have weak and nearly harmonic perturbation of the dielectric constant. So it's still periodic dielectric constant, but we assume that the dominant Fourier coefficients in the expansion of epsilon are epsilon 0, 0. So that's just 0th order Fourier coefficient, right? So calculated for n equal to 0, but I wrote epsilon 0, 0 so you don't mix it up with permittivity of vacuum. And then coefficients epsilon 1 and minus 1, which are just calculated for n equal to 1, right? So those are 0th and 1st order Fourier coefficients in the expansion of this function, okay? So I assume that these are the dominant ones. Epsilon 2, epsilon 3, epsilon 4 would have magnitude that is smaller than these. I also assume that the electric constant is real, which means that epsilon 1 and epsilon minus 1 are related as complex conjugates of each other, which wouldn't be the case if epsilon is not real, but we assume it's real. And actually this class, it's all real epsilon. We don't really care about absorption losses. We can neglect them pretty much all the time. So now, having this in mind, we can already kind of make the system of equations a little bit simpler. We can neglect Fourier coefficients that are corresponding to epsilon 2, epsilon 3, and so on, right? So we just keep epsilon 0, 0, epsilon 1, and epsilon minus 1 in these equations. So for this equation that we wrote here, if you remove everything other than epsilon 0, 0, epsilon 1, and epsilon minus 1, you obtain this, okay? So it's already a little bit simpler. Of course, I'm making approximations here, but this is a pretty good approximation for most problems that we're solving. And then, as in three-dimensional case, we also said that we could rewrite this for arbitrary k plus g, where g is arbitrary reciprocal lattice vector, and you can do that infinitely many times, but I'll just rewrite it for k plus 2 pi over a and k minus 2 pi over a. These are the most interesting ones because I'm already truncating it because of epsilon distribution, right? So this is the same equation rewritten for k minus 2 pi over a and k plus 2 pi over a. And I'm sure you can do this. You don't have to look at it very closely. This is just a very simple, exercise. Just replacing k minus 2 pi over a or k plus 2 pi over a instead of k. So going,
what kind of situation will this kind of approximation fail?
So this approximation, I mean, we may also ask you to look into this in homework, what is happening with actual periodic structures. But exactly, this would happen exactly if your dielectric constant is sinusoidal, for example. So you have some average value and you have sinusoidal perturbation on top. But in most realistic cases, also first Fourier coefficient is the strongest. So you take periodic function, and you calculate Fourier coefficients for that periodic function corresponding to permittivity, depending on, if you, for example, have some constant permittivity and you use laser interference to introduce periodic modulation on top, this is exactly the case because your epsilon is periodic, sinusoid, right? If your epsilon is just going between 1 and 3.5 because you're etching holes in your photonic crystal, then it's not exactly true, but epsilon 1 is still the dominant Fourier coefficient. Okay? Any other questions? Okay, so we have three equations that we wrote, right? We neglected everything other than the first and zeroth order Fourier coefficient. And we also rewrote it for k minus 2 pi over a, k plus 2 pi over a. What I will do now, instead of just writing homogeneous, I mean, this is already a homogeneous system of equations, right? And it's already truncated, but I will just express a of k minus 2 pi over a, and k of plus 2 pi over a from these three equations to see if I can actually truncate it further, right? So here it is. I'm just expressing from three equations that we had on the previous page, a of k minus 2 pi over a, and a of k plus 2 pi over a. Okay? Obviously, these equations are not really only constrained to these three coefficients. You see here, there is also k plus 4 pi over a and k minus 4 pi over a. But the reason why I'm doing this is because I'm trying to see under the conditions for which I'm solving this system of equations, whether I can make some more approximations and make things even simpler so I can solve them by hand here, right? And learn something interesting about the system. But the system is already truncated, so you can actually also solve this larger one. So here we go. What we would like to do today, hopefully by the end of the class, or if not, we'll continue next time, is see what is happening when k is roughly equal to pi over a. And when I asked you for the size of the first Brillouin zone, you told me it's 0 to pi to 1 times pi over a, right? So that's the irreducible first Brillouin zone. So k equal to pi over a, or roughly equal to pi over a, is the edge of the first Brillouin zone. And I'm interested what is happening there, okay? If you're interested in what is happening for another k halfway through, then what I'm gonna write on the next slide is not going to hold. But I'm interested specifically in this point because this is a high symmetry point. This is the edge of the Brillouin zone. This is where the band gap opens, and I want to see what's happening there so that I can calculate band edges at that point, okay? And this will lead to some more approximations because at this point, if you have a weak perturbation, right? And weak perturbation means that epsilon1 is much smaller in magnitude than epsilon00, right? So you're not making a very large perturbation. And as I said, that would exactly be the case where you're using laser interference to introduce periodic modulation of the electric constant, right? People do that on fibers or polymers, in which case the perturbation is not very large. And if that's the case, then you can write that around the Bragg condition, right? I mean, and we'll see that a little bit later in a moment, you are not going to open a very large band gap. The perturbation is going to change, it's going to open the band gap, but the relation between omega and k is not going to be very far from the relation that you will have between omega and k if you had a uniform medium with the electric constant equal to epsilon00, which is average value of the electric constant, okay? So if you have medium with some average value of the electric constant, let's say glass, right, or some polymer, then the relation between omega and k is just going to be given with the relation here, right? Omega divided by k is the speed of light in that medium, which is 1 over square root of mu naught epsilon00, okay? Then if you have your knob, which is your laser interference, you turn it on, that introduces perturbation on top of that, sinusoidal perturbation. That means that you're just cranking up that first order Fourier coefficient, epsilon1, right, which is introducing periodic modulation on the structure. And that's going to change things in the system, as we'll see in a moment. But again, it's not going to change them if the perturbation is not very large. It's not going to change them so dramatically that omega and k are very far from this condition, right? It's not going to be satisfied exactly, but omega and k are approximately going to be around that straight line corresponding to the propagation in the uniform medium, okay? And I'm doing this just to make my life simpler and get some relation that I can solve analytically, right? But if otherwise, you can also try to solve the problem, but it will be a little bit harder. Okay, so if this is the case, right, if k is approximately equal to pi over a, and you are around this Bragg condition, what happens? Well, from the first expression, if the perturbation is weak, right, you know that your k and omega times square root of mu naught epsilon00 are roughly equal. That's what we said, right? You're around this point. That means that the denominator of this first expression is around 0, which means that a of k is going to be very large, okay? And then when you look at the second expression, k is around pi over a and perturbation is weak. So if k is around pi over a, then k minus 2 pi over a is around minus pi over a, right? So this is still around pi over a and perturbation is weak, which means that this first expression and the second expression are again roughly the same, right? So denominator is again very small, which means that a of k minus 2 pi over a is also very large. But the third expression, here you have k, which is around pi over a. So this whole thing is around 3 pi over a. But the second number is around pi over a squared, right? So this here is not going to be 0, which means that k plus 2 pi over a is not as large as a of k and a of k minus 2 pi over a, right? So I'm doing this so that I can kind of simplify this system of equations even further, and I will neglect all the coefficients other than a of k and a of k minus 2 pi over a, right? Just so we get something that we can solve here in class, right? And here is the system truncated to only keep a of k and a of k minus 2 pi over a. It's written differently, but it's again homogeneous system of equations, right? That you can write as some 2 by 2 matrix and then multiplying vector, which is a of k and a of k minus 2 pi over a, okay? And that determinant of that matrix, which depends only on omega and k, is actually given here. For the system to have a non-trivial solution, a non-zero field, this has to be equal to 0. So what does this depend on? It depends only on k, right? Which is varying, but it's varying around pi over a. We picked that condition and made approximations for that. It depends on Fourier coefficients of epsilon. I mean, in this case, again, only on epsilon00, epsilon 1, epsilon minus 1, because we neglected all the others, and it depends on the frequency of the system. So when you calculate this determinant, you obtain a function of omega and k, which has to be equal to 0 in order to have a non-trivial solution for the field, okay? Does that make sense? I mean, this is a simplified example. You can do it in a not as simplified example, but this will give you combinations of omega and k for which non-trivial solutions of the field exist. So let's do this, right? This is basically dispersion relation. This is giving you combinations of omega and k for which you have Bloch modes. And keep in mind that this is all around pi over a, because we assume that we're looking into it around pi over a. I mean, you can assume that you're looking at it around different points, but we're looking at it around pi over a at the moment. If we're looking at it around pi over a, you can simplify it even further, because k minus 2 pi over a is around k as well. So this whole first term can be approximately written as square of the first term, right? First term times second term is the square of the first term, because k and k minus 2 pi over a are approximately the same. K is around pi over a. So this is a little bit simpler, right? So this has to be satisfied, and from here you can express omega as a function of k for when you have non-trivial solutions. And it turns out that this equation has, for each value of k that you pick, and again, this is a value of k around pi over a, it has two solutions, which we label as omega plus and minus, and these solutions are given here, okay? So omega plus minus is k divided by square root of mu naught epsilon 0, 0 minus plus epsilon 1. So if the periodic perturbation you're introducing in the system can be controlled with some magic knob, right? What are you controlling? You're controlling epsilon 1. Epsilon 0 is just the average value of the electric constant. If you remove your periodic perturbation, what is the dispersion in your system? Omega is k divided by square root of mu naught epsilon 0, 0, right? It's a straight line. But then if you turn the perturbation on, meaning you crank up your Fourier coefficient epsilon 1, two solutions pop up. That's not the solution for your omega k anymore. Instead, you have one point, which is above that first solution, right? So that would be omega plus, which is k divided by square root of mu naught epsilon 0, 0 minus epsilon 1. And the other one would be divided by square root of mu naught epsilon 0, 0 plus epsilon 1. So the larger the first order Fourier coefficient, which means the larger the perturbation, the larger the separation between these 2 points. These 2 points are edges of the photonic band gap, and we'll prove that there are no solutions, real solutions, non-evanescent solutions for the field between these 2 points. So the separation between these 2 points, which is omega plus minus omega minus, gives you the size of the photonic band gap. And if you were to calculate it, you will see that that's delta omega, or omega plus minus omega minus, can also be approximated as the central frequency of the band gap, which is that frequency that you would have if there was no perturbation, times magnitude of first order Fourier coefficient divided by magnitude of the 0th order Fourier coefficient, right? And you just obtain this by subtracting the solution for omega plus and omega minus, and you use the approximation that 1 over square root of 1 plus alpha, when alpha is something small, is approximately the same as 1 minus alpha half, right? So it's a very well-known expression. So the size of the band gap depends on the central frequency. The central frequency, again, is here for the edge of the Brillouin zone, k divided by square root of mu naught epsilon 0, 0, average value of the electric constant. We're working around k equal to pi over a, right, around the edge of the Brillouin zone. And if you crank up the perturbation, increase the size of the photonic, increase the size of the perturbation by increasing the size of the first order Fourier coefficient epsilon 1, you will also increase the size of the photonic band gap, or separation between these 2 frequencies. That's not surprising, right? Because you know that you need some perturbation in order to build photonic crystal or photonic band gap. In the cartoon image, all of these reflectivities from interfaces have to add up in phase in order to build large reflectivity in the direction of propagation or to build a photonic band gap. So it's not surprising that you need larger perturbation in order to open a band gap, right? If there is no perturbation, there is no band gap. It's just propagating through uniform medium. You may have seen this expression before in condensed matter physics when you calculated, again, Schrödinger equation for a periodic potential. You may have derived that the size of the band gap depends as approximately as the Fourier coefficient, first Fourier coefficient of the periodic potential, right? And that's exactly the same conclusion. Any questions about this? So just yeah, go on.
Sorry, that plot is like using more terms, right? Because they plot from like 0 to pi over a.
Yes, absolutely. So the only thing, and I'll summarize that, the only thing that I'm doing here, I mean, from the equations that I wrote them around k equal to pi over a, and we'll see, you know, exactly what is going on outside. Well, we know outside that it has to be periodically repeated, right? We know that because we proved already that all the solutions inside of the first Brillouin zone are just repeating periodically in space. So whatever I have from minus pi over a to pi plus pi over a has to be periodically repeated. By symmetry, we can prove that minus pi over a to 0 and 0 to pi over a are the same, right? So I'm just plotting 0 to pi over a here. But master equation that I wrote was for k equal to pi over a, or not exactly, k approximately equal to pi over a. So all that I solved was, I'm not sure if you see my pointer, this region here around pi over a, right? And I found omega minus and omega plus. That's all that I solved. If you were wanting to solve it for k equal to 0, you can from master equation, but it's not the approximations that I wrote before. Okay?
Yeah, okay.
Okay, yeah. And we found omega, but this is fine if you are interested in looking for the size of the band gap. So we found omega minus and omega plus. So if you turn down the perturbation, right, we know in this region that omega and k would basically be along the straight line, which has a slope given by omega epsilon 0, 0, average value of the electron constant, right? If I turn the perturbation on, which for us is first Fourier coefficient epsilon 1, then instead of having a solution that omega 0 and kz are on this straight line with the slope given by epsilon 0, 0, you instead of that have two solutions, omega minus and omega plus, right? And you know, we'll see how when we unroll this band diagram, it looks outside of these points, but for now, we're just focusing on this region, okay? Any other questions? Okay, so we have like 2 more minutes here. So I don't want to go much further, just to set up the stage for the next time, right? So again, going back to Alex's question, all that we did is we solve using master equation, the band diagram for the region around pi over a, edge of the Brillouin zone. We found that there are solutions at pi over a, which are equal to omega minus omega plus. You could actually use the same system of equations to find solutions for k around this point, but the further you go from it, the approximations that you made would not hold, right? So it's just that region there. And I said this would be the solutions for this problem when you have a perturbation, but I didn't really formally prove that there are no solutions between omega minus and omega plus. We calculated size of the band gap, but I didn't really prove there are no solutions between omega minus and omega plus, okay? So what I will do next time is we will pick frequency between omega minus and omega plus, right? Let's say omega 0, which I know should be between them. That's the frequency that if we have without perturbation. And I plug that back into master equation, and I will see that for whatever frequency between omega minus and omega plus that you plug into master equation, you will obtain complex k as a solution. What does that mean? Complex k. I mean, here I plot real k, right? Complex k would mean that you still have solutions that look like normal modes or Bloch modes, but they would correspond to complex k vector, which means that they would be evanescently decaying Bloch modes, okay? So to be more accurate, right, when we plot these band diagrams, we know, and we plot them inside of the irreducible Brillouin zone, we know that each point on this diagram, if you actually pick any omega k point along the diagram where you plot a line, that means that there are real Bloch modes that correspond to that. Those are propagating Bloch modes. But inside of the points corresponding to the photonic band gap, there will still be solutions that would have the shape of the Bloch modes, but they would correspond to complex k, which means that they would be evanescently decaying. And actually, if you go back to the very beginning of our presentation, when we were looking into what happens when you excite, and we're finishing up. So it's just want to go back to that movie that I repeated today and I showed you in class last week. You remember this, when we actually excite the structure with something that's inside of the photonic band gap and you look into what happens inside of the structure, I mean, the solution, there is still non-zero field inside of the structure, right? But that non-zero field is evanescently decaying. So that non-zero field could be decomposed into evanescently decaying Bloch modes. But if you have a propagating field, then you would have propagating Bloch modes that would look something like these field plots that we have here, and we'll discuss them a little bit later. And they're not evanescently decaying. They correspond to real decay. Okay? Unless there are more questions, it's 2:50, so we should probably wrap up. Have a good weekend, folks. I'll see you on Tuesday. Bye.
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 Bye-bye.